Hello and welcome to the course, Design Bore Fields with Confidence. This is the second chapter of the fifth part, and we will be talking again about the hydraulic insights when designing bore fields. And in this chapter we will do this based on the seemingly simple question, which one is better, a single or a W tube? Now again, as a disclaimer, I know there are other solutions as well and some innovative probes. We will cover them later in this course. But for now, let's focus on this misleading question and see what insights we can get from that. Now, what you see here on the slide is the equation of the total pressure drop, and which was introduced in the first chapter of the last part. And to recap, what we see here is the sum of the friction losses and the F, the friction factor, multiplied by the pipe length divided by the diameter, and also the sum of all the local losses multiplied by the fluid density and the velocity squared divided by 2. And we said there were some relationships to be found in this equation. And one relationship is that the pressure drop is proportional to the pipe length. That's when our pipe length increases, so does our pressure drop. And the second relationship was that the pressure drop was quadratically proportional to the velocity squared, meaning that if our velocity doubled, also our pressure drop increases with a factor of 4. Now, we also said that we do not care about this velocity in and of itself. Typically, it's the flow rate we care about. And there is a relationship between the velocity of the fluid and the flow rate, which is also linear. And then we see that there is a relationship between the velocity and the pipe diameter, which is inversely proportional to the square of the diameter. And if we put this all in our general equation, we see that our overall relationships show us that our pressure drop is quadratically proportional to the flow rate, which you can also see on this graph to the left of the slide. This is typically quadratic shape. And we also see a very strong relationship between our pressure drop and our pipe diameter. We see that the pressure drop is inversely proportional to the diameter to the fifth power, which is a very strong relationship indeed. Now, with this freshened up, let us take a look at this question, single versus W tube. And we will tackle this by looking at 3 different cases. And we will start with the basic case, just keeping the pipe diameter the same but changing the number of pipes from a single to a W. Next, what we will do as a side track is say, okay, let's keep the number of pipes now the same at both a single U, but change the diameter and see what the effect of that is. And then the third option is that we combine both. So we change the diameter as well as the number of pipes to come to an overall conclusion on which one is better from a hydraulic perspective, single or the W. Now let's start with the very beginning. If we keep the pipe diameter the same and we change the number of pipes, so in this case from a single DN32 towards a double DN32, we see that from a hydraulic perspective, our double DN32 is always better. And this is simply because, well, we have our flow rate going to our borehole. In the case of a single U, it has to pass through that single U. So one U-tube gets 100% of the flow rate. If we have a W, it only gets half. So in that case, in the case of a single U, the velocity is twice as high, meaning the pressure drop is a factor 4 higher than in our W. So this is a very clear result. Now what is interesting is if we compare this to the thermal insights that we discussed in the last chapter, and that you see here, so we have our thermal counterpart, we see that there is a region, that there are flow rates where our W has a better borehole resistance and better thermal behavior, let's say, and that in these same flow rates, it's also better from a hydraulic perspective. So from 0.1 liters per second to 0.25 and from 0.45 liters and higher, we see that our W is the best solution both thermally and hydraulically. If we take a look at a single U, and we see that it's thermally the best, between 0.25 liters per second and 0.4, and it has the lower borehole resistance there, but it will always have a higher pressure drop. So for the single U case, there is no situation in which it's both thermally better and hydraulically better. So that's the first insight. Now, let's keep now the number of pipes the same, both a single U, and let's change the pipe diameter. And that you see here. And we compare now a single DN32 with a single DN40. And what you see is that our DN40 has, again, always a lower pressure drop, and significantly lower. And that's because our relationship we discussed earlier, if we increase the diameter with a factor of y, then our pressure drop decreases with 1 over y to the power of 5. So a very strong relationship with the pipe diameter, which is clearly visible here. Now if we take a look again at the thermal counterpart, we see here a little bit the same as before, that there is a region in which our single DN40 is better from a thermal perspective, and because we have now a larger surface area, and we discussed that last chapter. And also for this case, we have these flow rates, we have a better pressure drop. So again here, there are some situations in which our bigger diameter is better both thermally and hydraulically. For a single DN32, it's not the case. It's better in some small range here from a thermal perspective, due to the turbulence that starts earlier and so forth, but not from a hydraulic perspective. Now if we mix these two cases up and we compare a single DN32 with a double DN32 and a single DN40, we get this result. And what's immediately visible to the eye is that our single DN40, the pressure drop from it, and the double DN32, it's more or less the same. And especially in this beginning, when both are laminar, we even see that our single smooth probe, DN40, has the lowest pressure drop of them all. And that's because when we have a DN40, a single one, the contact area, where there is friction between the fluid and the pipe, is actually smaller than with our double DN32. So in the double DN32, the fluid has more contact area to have friction with the pipe, meaning that it has a higher pressure drop. Now, when we start getting turbulent, the situation changes a little bit, and that's why both lines deviate towards higher flow rates. But it's more or less the same. What is interesting is that our single DN32, it's the worst kit in the class. It decreases incredibly. It has very clearly the highest pressure drop. Now let's again compare this to the thermal counterpart, because here things are getting interesting. Because if we think about, okay, let's say we start with the double DN32, and we see, okay, it's clearly better in this case, between 0.1 and 0.25 liters per second. But if we look at the hydraulic counterpart, that's no longer the case. So if we mix both single and W and pipe diameters in the same question, let's say, or we broaden the scope, then it's not the case that our W is always better from a thermal and hydraulic perspective. Because in this case, from a hydraulic perspective, the single DN40 is better. And from a thermal perspective, the double DN32. So it just depends on what you're looking at. And be aware that this difference in pressure drop and so forth, from very deep boreholes, 300, 400, 500 meters and so forth, it can become really, really important to see which pipe diameter you have. And also your pump energy will play a role. And to illustrate that, let's talk about this pump energy for a second, because having a larger pressure drop means that you will have more pump electricity consumption. You require more pump energy. And we already discussed that in chapter 2 of the last part, but in this table I summarized it for these three cases. So the single DN32, the single DN40, and the double DN32. Both for a constant flow rate. And what you see here, all the results are, by the way, again in the textbook, is that a single DN32, it's turbulent. And the Reynolds number is above 2300, so it has the highest pressure drop and the highest electricity consumption for the circulation pump, around 26 kilowatt hours per year in case of a constant flow rate. If we go to the single DN40 or the double DN32, we are both laminar, below the 2300 Reynolds number, and the pressure drop is hence also significantly lower, as is the yearly electricity consumption. And what is interesting here is that from a pump point of view, from a pump electricity consumption perspective, our single DM40 is the better solution when compared to the double DM32. And that's because we have a different contact area, again, as we explained earlier, meaning that we have less friction and the pressure drop is lower in this case. Now, this was for, let's say, the peak flow rate, but when we're working with modulating circulation pumps, we know that our flow rate is not constant over time. So if you now compare this to the situation of 70% part load, and there you see we have not 0.3 liters per second, but we have 0.21 liters per second, and all the situations are laminar. Meaning that yes, our single DM40 and DM32, they decrease again a little bit in pressure drop and yearly electricity consumption. But most importantly, our single U, it falls back significantly. It more than halves. And also the pump electricity consumption goes from 26 to 7. So let's say it's still the worst kit in class, but it's already acceptable. So when talking about this pressure drops and saying, well, the single U, it has the highest pressure drop, that's true. But if you look at it from pump energy consumption point of view, where we have different flow rates, the difference is actually not that pronounced or significant, I would say. So that's as a little bit of nuance. Now let's jump into GHE2 and show this difference also for a real case, an auditorium building, where we will be comparing these three different probe designs, probe selections, and compare it with a constant versus a variable flow rate. So here we are in GHE2 Cloud. I created a new project with these three different options, the W, single U, and single DM40. Now, if you want to follow along, again, you can download the report from this project over on our website, and you can try recreating what we will be doing here. It's a situation with active cooling in auditorium, quite a lot of cooling demand, 25 degrees as a maximum. And whenever we're interested in getting the hydraulic information and the pump electricity consumption, it's important to say, yes, I want to calculate the pressure drop of the bore field. Now, the horizontal connections, we do not really care about at the moment. It's just this pump efficiency that will get us to the electricity consumption. So let's keep everything to the default value, shall we? It will be 8 boreholes of 150 meters borehole depth. Set a double DM32, monopropylene glycol 25%, and a constant temperature difference. So basically, every hour, our pressure drop will be calculated, as well as our thermal effects. So this is with an hourly varying flow rate, and our thermal demand, active cooling, SEER5, and our auditorium load profile. And if we go to the results, we see here thermally we're beautifully within the limits, but you can already see, if we scroll down, our cooling demand is significantly higher than our heating demand. It's 90 kilowatts when compared to only 30. And this also reflects in the hydraulic option. So in extraction during heating, we only need 1.6 liters per second, but really the cooling demand is here the most important. It's around 6.8 liters per second of flow rate that we have. And as you can see, most of the year it's rather low, and then in cooling we have this high peaks in pressure drop. We also see the same here in our thermal aspects as well, of course. Now, what is important here for the pump energy consumption is that although we have this very high peaks and we need 120 kilopascals of the pump head to make sure that the flow can be pumped through the system, the pump energy consumption is actually way lower, because on average the pressure drop is just, was it around 15 or something like that. If we zoom in, it goes down and it goes up and so forth. Now that's for the W. If we go to the single U, quite a lot changes, and what's immediately noticeable is that the pressure drop explodes. It goes to 400 kPa or 385 kPa, but the electricity consumption goes from 37 to 83 kilowatts hours per year. So that's not that much of a difference, and that's exactly what we talked about just before, is that, yes, if you look at the worst case, the peak situation, and we will show that in a second if we jump to constant flow rate. Yes, there is a very significant difference, but on average, we go from 37 to 83 kilowatt hours per year of electricity consumption. And yes, it's indeed a factor 2 of difference. But what is important, if we scroll down and you see what is the total electricity consumption, yeah, it's 2 orders of magnitude higher. So it does not really matter in this case, or it does matter, but it's always important to put things into perspective. Now, from the thermal aspects, you can see here that our borehole resistance is worse than before, because in RW we were already turbulent. So our borehole resistance and injection was as good as it can get. A turbulent W is very, very good. Now we go to an insanely turbulent single U, which is even better, but the problem is that now we have only 1 U-tube to exchange heat instead of 2, making this in the end a worse effective borehole thermal resistance, as well as we cross the limits in this case. Now if we jump to using a single DM40, what you see is that our pressure drop, our Reynolds number goes down a little bit. Borehole resistance is again a little better, because now we have a little bit more surface area. A DN40 has a bigger outer surface than a DN32, so a little bit better heat transfer. Not as good as a W in this case. And if we go down to the pressure drop, what we see is that it's actually lower than our W. So it was 37, here it's 32. Although our peak is higher, the pressure drop in the worst case condition is higher than the W, but now our average energy consumption is a little bit lower. And that's because in this initial range, when we're quite a lot of laminar flow, our single DN40, because it has a bigger diameter, has less surface area for the fluid to have contact with, meaning that we there have, in these regions, a slightly lower pressure drop, meaning that on average, our DN40 will consume less electricity than our double DN32. We cross the limit a little bit here for this design, but you can already see that depending on your particular situation, it can happen that the single DN40 is actually better thermally and hydraulically. So that's very interesting indeed. Now, we have a flow rate of 6.79 liters per second. Let me go ahead and duplicate this scenario to actually show the difference in pump energy consumption. So let's go to constant flow rate, shall we? 6.79 liters per second through the entire bore field. So let us go ahead and calculate that. And that's the advantage of having a cloud tool. We can let it calculate in the backend and continue changing our different scenarios. 6.79 liters per second. And here again, constant flow liters per second. So if we now go to the W, what you see here is that our pump energy, it's significantly higher. It's from 37 to 8,000 kilowatt hours. And that's because, you can clearly see it here, the pressure drop is now always high. We always have this very high flow rate, although we do not need it for extraction. So our pump is just working. And if we compare this 8,000 kilowatt hours to the total electricity need, it's in the same order of magnitude. So that's actually not a very good thing. Our pump is just consuming way too much electricity. So in this case, please use a variable flow rate frequency controlled pump, because it will save you a ton of money when operating the system. If we go to a single U, situation is even worse. We go to 26 megawatt hours of electricity consumption for a circulation pump, which is absolutely not what we want. And then if we go to the single DM40, it's 9,000. It's a little bit higher than a W, and that's because now, well, we're always turbulent. And as we said before in these graphs, when we're turbulent, our DM40 is a little bit worse than our DM32. So that's why we now have this high electricity consumption as well. But this is for the constant flow rate. If we go for the frequency controlled one, the difference is noticeable, but in the overall energy picture, not that significant. So that's what I wanted to give you, or insights I wanted to share with you when we're talking about single versus W probe from the hydraulic perspective. And as you can see, again, here there is no definitive conclusion. It really depends on your situation. There is a definitive conclusion between working with constant and variable flow rate. Please work with variable for pump energy consumption. But from which one is definitely better, it really depends on your situation, and it's important to simulate different situations as well. Now, this was what I wanted to say in these two chapters about single versus double. We will revisit it when we will be talking about the innovative probe designs. But in the next chapter, we will look at some other insights we can get when we're now changing the bore field design and when we're comparing our traditional rectangular configurations with actual as-built situations, so where the boreholes are not located at a specific grid configuration. I'm looking forward to seeing you in this next chapter.